In this exercise, we are learning how to derive some details out of an airline schedule. Traditionally, airline schedules are stored and exchanged using the SSIM or SIM schedule format. SSIM is the abbreviation for Standard Schedule Information Manual, and it describes a standardized schedule format defined by IATA. Purpose of this standard is to enable a joint data exchange supporting the electronic transfer, handling, and processing of schedule data. SIM schedule is provided in form of a plain text file with fixed columns for different data fields. In this video, we are not dealing with the question how to import a SIM schedule into Excel or database management system, but we start straight with an extract of the provided data in form of an Excel workbook. In our Excel file, we have the following data fields given. In column A, we find the IATA airline designator, followed by the flight number in column B. The flight number can be any number from 1 up to 9,999. The itinerary variation identifier numbers the different variations of a flight, and the leg sequence number counts the physical sequence of multi-leg flights. Column E provides the service type, which allows us to identify, for instance, passenger versus cargo flights. The next two columns inform us about the period of schedule validity for each flight, followed by the departure and arrival point, given in form of a 3-letter IATA airport code. The aircraft type field lists the aircraft used, and the days of operations tell us on which days a flight is operated. Days of operations are numbered from 1 to 7, with Monday being day 1. Column L and M inform us about the local departure and arrival time, and the last two columns specify the UTC differences for the arrival and departure point. If UTC time is earlier than local time, the UTC difference is positive. Otherwise, it's negative. Using this schedule data, we are answering the following questions. First, we count the number of destinations served in the schedule. To count the number of destinations served in the schedule, we copy first all departure points to an empty column in a new sheet and append afterwards the arrival point list. Theoretically, it would have been enough to look at the departure points only, as every departure point is also an arrival point sooner or later. Next, we go to the Data tab and click Remove Duplicates from the Data Tools group. 23 different destinations are served. Next, we count the number of operated routes. Counting the number of routes works in a similar way, with the only difference that we copy this time the departure and arrival point columns simultaneously to a new sheet. We select both columns and click Remove Duplicates, and 44 different routes remain. Determine the UTC departure and arrival time for each flight. Before we start with any calculations, let's have a look at the basics of UTC offsets. The world is split in different time zones in which residents have the same local time. Each of these time zones has a certain offset in hours and minutes from the so-called Coordinated Universal Time, or short UTC, which is the time at the prime meridian. West of the prime meridian, the UTC offsets are negative, while east of the prime meridian, they are positive. Chicago, for instance, has an UTC offset of -6 hours, while Shanghai has an UTC offset of +8 hours. To convert local time in UTC time, we need to subtract the UTC offset from the local time. 8 o'clock Chicago local time in the morning therefore is equivalent to 1400 UTC time, or 2200 local time converts into 4 o'clock in the morning. The same calculations for Shanghai reveals the following. 7 o'clock local time is equal to 2300 considering the offset of plus 8 hours. And 2100 local time converts to 1300 UTC time. In case UTC times are given and we're interested in the corresponding local time, calculations obviously work in the opposite direction. Thus, we need to add the UTC offset to the UTC time to get the local time as a result. Before we can start applying this knowledge to our Excel's exercise, one more important comment. Excel is by default not able to handle negative times, which is however a feature we need for negative UTC offsets. To work with negative times, we have to change Excel's default date system for the Excel workbook in which we want to use negative time values. For this, we need to click the File tab, select Options, and click Advanced from the left pane. In the right box, we scroll down until we arrive at the section When calculating this workbook. Here we check Use 1904 Date System. As we can see, I selected this option already for the given workbook. Once we click OK, Excel displays negative times. The disadvantage of this modification, however, is that Excel dates in this workbook are not any longer compatible with dates in other Excel workbooks. It would lead too far at this stage to explain the details, but everyone who's interested should search the web for Excel's 1904 date system. To calculate the UTC departure and arrival time in Excel for each flight, we need to subtract the UTC difference from the local time. Depending on the local time and whether the UTC difference is positive or negative, this results in a UTC time which is either on the same, the previous, or the next day. UTC times on the same as well as next day are perfectly handled by Excel. For UTC times on the previous day, the mathematical result of our calculation is negative. To turn it into a correct time of day value, we need to add 24 hours in this case. We had already a similar situation in one of the previous exercises and know already how to deal with this situation. We use an if function to check if our mathematical result is positive. If this is true, we subtract the UTC difference from the local time. In all other cases, we need to add 1, which represents 24 hours, to this formula, and voila, the UTC time is calculated. Identify the city names of all destinations served. Looking at the 3 letter codes of the 23 destinations served, we do find quite some exotic airport codes. To match these airport codes with the belonging city names, we can use the lookup table provided in the lookup datasheet. Here we find a list with 122 3-letter codes, city names, and latitude-longitude information. I hope that nobody thinks about adding the city names by hand to our destination list, but we use Excel's XLOOKUP function instead. XLOOKUP finds matching airport codes from our destination list within the lookup list and delivers the city name as a result. We enter the XLOOKUP function, and the first argument we need to specify is the lookup value. This is in our case the first 3-letter code in cell A2, for which we want to find the city name. Next, we need to specify the lookup array. This is the range of values A2 to A123 in our lookup data sheet, in which Excel is supposed to search for matching values. The last argument we need to enter is the return array, which allows us to select the values the xlookup function is supposed to return in case of a matching 3-letter code. As we are interested in the city name, we select the range B2 to B123. Don't forget to use absolute cell references for the lookup and return array. As all other arguments are optional, we close the bracket, hit enter, and get instantly the city names for all our 3-letter codes. If we want to get additionally also the latitude-longitude data for each 3-letter code, we simply need to extend the return array up to column D, and automatically we get the latitude-longitude data as well. The predecessor of the xlookup function was the vlookup function in Excel. But since xlookup is much more flexible than vlookup, I recommend to use xlookup only. Visualize the destination portfolio on a map. To visualize the destinations on a map, we can use the 3D map tool in Excel. We select our data, go to the Insert tab, and click 3D map. Excel opens the map tool and automatically plots the cities as it recognizes our coordinate values. Alternatively, it would have worked with city names alone as well. If you would like to learn more about 3D map in Excel, follow the link to the belonging video. To get all 23 destinations displayed, let's change the layout to a flat map, zoom out, and increase the size of each marker. Some versions of Excel do not provide the 3D map tool. In this case, I recommend to use, for instance, Google Maps instead. Calculate the frequency per route. Calculating the frequency per route requires that we translate the ops days field into a frequency number. For this purpose, we create 7 new column headers and label them day 1 to day 7. Next, we check for every day of the week whether the flight is operated on that day or not. A flight takes place if the belonging weekday number is listed in the ops day pattern. To check this, we use the mid function and, starting with Monday, we extract the first character from the pattern. As we get 1 as a result, we learn that the flight operates on Monday. Next, we repeat the same steps for Tuesday. The only thing we need to change within our mid function is that we extract the information for day 2 from the second position of the ops day pattern. In principle, we could continue to update the mid function in the same way for the remaining days. But let's use a more elegant version. If we look at the header, we see that the number which represents every weekday is part of the header name. Thus, we can grab it from there to use it within our mid function. Let's go back to day 1 and replace the second argument of our mid function by the right function, which we use to extract the rightmost character of cell R1. To be able to paste the formula to the remaining days, we need to set an absolute reference to the row indicator. Additionally, we need to log the column indicator K of our first argument. With these changes, we can now copy and paste the formula to the right and get a drilled down version of the ops day pattern for every day of the week. The next step is to translate this result into frequencies per flight and per route. Every number from 1 to 7 in column R2X represents a single flight, while a period tells us that no flight takes place. By means of an if function, we can transfer any number output of the mid function to the value 1. In all other cases, it's supposed to return 0. We implement this by the logical test that the extracted character is a period. If this is true, the if function returns 0 and the value 1 otherwise. In column Y, we can now sum up the values from column R to X and know what the frequency per flight is. Finally, we create a pivot table report to sum up the frequencies per route. Summarize the offered seats per route. In the SIM schedule, no information about provided seats is given, but information about the used aircraft type. Additionally, we have lookup details regarding the available seats given for the 3 aircraft types used in the schedule. If you've understood how to answer the previous questions, then answering this question should not be a challenge. Therefore, my recommendation is to pause the video and try it by yourself. To answer this question, we use the XLOOKUP function again to look for matching aircraft type codes in our schedule and in the lookup datasheet. Whenever we find a match, the number of seats are to be returned. Once we have the seats per row, we can now sum up the seats per route using a pivot table. Calculate the available seat kilometers. To calculate the available seat kilometers, or ASK, we do need to know additionally the distance per route. In a later exercise, I'm going to show you how to calculate distances using the Great Circle Distance formula. For this task, however, we use the lookup values from our lookup datasheet. We enter the XLOOKUP function and specify as first argument the range of values in both columns H and I, separated by an ampersand. As lookup array, we select columns H and I in the lookup sheet, also separated by an ampersand. For the return array, we select the range of values in column J. Note that XLOOKUP allows us to search for a combined lookup value. To calculate the ASK next, we multiply frequencies by seats and distance and get the ASK per flight. The sum of the single ASK values per row are the total available seat kilometers.